In this particular demonstration, we're going to get a great look at a spontaneous exothermic reaction that's actually used in rocketry. It's a very simple reaction. We're going to do the reaction between hydrogen gas and oxygen gas in a stoichiometric mixture, as indicated by the reaction, to form water in the gas phase. The standard enthalpy of reaction for this reaction is minus 484 kilojoules. The negative sign on this indicates to us that the reaction is exothermic. But now let's look at the spontaneity of this reaction as well. We know that the delta G is equal to the delta H minus T delta S. Now we notice on the delta S for the reaction that we are going from 3 moles of gas to only 2 moles of gas. So the delta S is actually negative for this particular reaction. However, the delta H is so overwhelmingly negative at this particular at room temperature that the delta G for the reaction is also negative. The negative delta G for the reaction tells us that the reaction is going to be spontaneous. Now you might be thinking, well, if there's oxygen and hydrogen in this Coke bottle, why aren't they reacting to form water? Essentially, for all practical purposes, none of them are actually doing that right now because none of them have enough energy to actually, when they collide with each other, to form the water. Now, it should make sense to you on a molecular level that in order to have a chemical reaction like this, the molecules have to collide with each other. Although we are in the gas phase and the molecules are quite far apart, they're still undergoing many, many collisions per second. In fact, if we could piggyback on any one of these molecules in the Coke bottle, at room temperature, they're hitting one of their buddies about 1 billion times every second. But right now, none of them are hitting hard enough to actually do anything. But we're going to change that right now. We're going to light a match to it. And Wally's going to help me with this. It's kind of a two-person demonstration here. This reaction is pretty violent and it makes a lot of noise. And so Wally's going to put on his ear protection, and I'm going to cover my ears when we do this. So go ahead and put those on.
No problem. And
you'll be able to hear me okay. Now, he's going to provide the activation energy with the match here. And so when I give you the signal, I'd like you to light the match. And then once I see the match is lit, you're going to see me take the stopper off the bottle. You're going to watch me cover my ears. And then you're going to hold the lit match horizontally over the lip of the bottle and try not to let go. Again, this is going to make a very loud noise. It's going to make an explosion, so I'm going to be covering my ears. And if you ever do this experiment yourself live like this, you definitely want to have ear protection on. So again, when I tell you to light the match, you will light it. I'll remove the stopper. You'll watch me cover my ears and just hold it over the lip until something happens. Okay, and we're going to dim the lights here, so it'll be a little bit easier. We'll let our eyes adjust. Go ahead and light the match. I'm going to remove the stopper, wait till I cover my ears. Go ahead. Very nicely done. You can set the match on the bench. I'm going to turn the lights back on and you can have a seat, Wally. We can see a very, very rapid reaction. Hopefully you were able to see here, you might have saw a little bit of orange coming there. The orange is probably the match getting blown out, but you get kind of a whitish blue flame coming out of there. It's a very, very hot chemical reaction. You'll probably have a flame temperature of around 4,000 degrees Kelvin. That's certainly hot enough to melt metal. Now, what type of thing would this reaction be good for? This is a classic rocket reaction like they used on the main rocket engines of the space shuttle. And when the space shuttle was operational, they used liquefied hydrogen and liquefied oxygen in order to minimize the size of the tanks. Even then, the tanks were very, very large. The large external orange tank on the shuttle was the container for the liquid hydrogen and oxygen. So it was bigger than the shuttle itself. It takes a tremendous amount of rocket propellant to launch something as big as the shuttle into orbit. The amount of hydrogen and oxygen they had in there was about 1 billion times what we had in the Coke bottle, so it makes a pretty loud noise when it's coming out of there. If we link this to the concept of the equilibrium constant, the K sub P, that is the equilibrium constant in terms of the partial pressure of the gases, has an equilibrium constant of about 10 to the 80th power. Of course, what that tells you is that at equilibrium, which the reaction got to very, very quickly, the products are grossly favored. So for all practical purposes, absolutely nothing goes back into this form. In other words, you do not expect water at room temperature to spontaneously decompose into hydrogen and oxygen gas. It goes completely to water once we have the activation energy. As you might imagine, when you use it for a rocket engine, you don't have somebody standing underneath the engines with a match to ignite the propellant. They'll use some sort of an electronic ignition system. Some are simple, some are kind of complicated, that will provide that match, the spark, if you will, that will start the rocket engines here. The disadvantage of a system like this is that the flame will destroy the igniter system on the engine, so if you have to shut the engines down, you won't be able to start it up again until you refurbish the igniter. So this particular reaction is a great example of what we refer to as a spontaneous reaction, because the delta G is negative, very exothermic reaction as well.